Hey there. Welcome to the 10th and final week of the RoboChargers CAD class and our little Onshape segments here. This week we're going to be going back and doing one final project. Um, it's a little bit more complicated than what we've done before. We're going to touch on a few new concepts and also just kind of get some general practice in doing some of the same things that we've been doing this entire time. So this is a relatively large project, but we're not going to split it into 2 weeks. Um, at this point, in the class, you guys have gotten some practice, and you should be a little faster at some of the different skills that we've gone over. So basically, we're going to just do this entire project in one go this week. So this will be a little bit of a longer session. I'm going to break this into several different parts just to kind of make the consumption a little bit more palatable. But do expect to spend a little bit more time on this project than you've spent in weeks before. So let's go ahead and jump into it here. Let's create a document for week 10. So what we're going to be designing is kind of the front portion of basically a motor-driven roller. It's going to be driven by some timing belts. We talked about timing belts, I believe, in week 9 in our COTS highlight. We're going to be kind of going over how to design with belts. A lot of the concepts we're going to talk about here also apply to chain, but we're not going to really touch on chain today as much. This system that we're going to design is pretty specific in terms of design style to the RoboChargers. So if you're watching this video and you're on a different team, the way that you would build this type of a mechanism may be significantly different. These types of mechanisms with these rollers and everything vary significantly team to team. So I'm going to show basically the way that the RoboChargers would build this mechanism, and just to kind of understand that that might not necessarily be the same for every team. In addition, this mechanism specifically is going to be kind of targeted towards intakes, like roller intakes. However, you can also build rollers the same way for little rollers inside the robot for serializing or indexing or whatever you might need a roller for. So that's really the real reason that we're going over this project this week, is because designing around rollers and stuff is a pretty general purpose design task in FRC. You'll see it a lot. And the concepts that we're talking about here also apply to FTC as well. So we're going to start off the same way we have in the past. We're going to start off with a layout sketch, and then we'll kind of move onwards from there. So what we're going to do is we're going to I'm not going to worry too much about how the rollers are positioned, just because that's going to be defined by the robot design, and we don't have a robot for this to go with. So I'm going to kind of do something that's kind of general purpose. It's a little bit kind of an average representation, but I'm not going to care too much about where the rollers are positioned exactly, because we don't have a specific application in mind. So we need to attach something to the origin here. So I'm going to just say that the motor driving this whole system is going to be positioned at the origin. That's pretty arbitrary. I just need to put something there to anchor off of. So this is going to be our layout sketch. So I'm going to use this as kind of the to this. I'm gonna start sketching in some geometry here that we know basically. So this first circle is going to be the motor. We're going to use a Neo to drive this. And then we're going to have 2 rollers that are powered off of the motor. So there's not going to be a roller where the motor is. And then essentially we're going to have a belt reduction from the motor to the first roller. And then we're going to have a roller here, and then this roller is going to have a second belt on it that's going to drive a third roller. And we're going to kind of just put a little bit of an angle in this as well. There's no real reason for this angle, but typically when you're doing intakes, all of the rollers aren't in a straight line. There's kind of a bend to them. So I want to kind of show how that works. In addition to that, we're going to be driving the last roller will be on a dead axle. I'll explain a little bit more about how that um, is going to be built as we get a little farther along. But you guys will remember pretty early in the CAD class, in like one of our first 2 or 3 weeks, we talked about what the difference between live and dead axle is. So you can go back and review that if you need a little refresher. But I'll kind of explain a little bit more as we go, so you don't really need to worry about it. So then this roller out here at the end will be dead axle. That would be a pretty typical arrangement for a well-built intake. There are a lot of teams that don't do that. However, there's a lot of benefits to using dead axle, especially on the front roller of an intake. Generally speaking, it would be a good idea to do dead axle rollers everywhere if you can. There aren't that many disadvantages to dead axle rollers, except there's just a slight, it's a little bit more design effort up front, basically. So the rollers we're going to be using are 1.25, I believe, is what we're going to use. We'll look up the plastic before we commit to this dimension, but it's just a polycarbonate tubing, round tubing that we order from McMaster. And so there's going to be a belt that goes from the motor to this roller, and then a belt that goes from this roller to this roller. Now, what we want to do is get a little bit of a speed reduction from the motor to this roller. We don't want to run these one-to-one at the speed of the motor. We want a little bit of a gear reduction. So we're going to do that with the belt. If you were using this on a roller inside your robot that you wanted to be a little bit more, slower and more controlled or something, you might need to put a gearbox on the motor. The belt might not be enough reduction. But for an intake, you typically want to run intakes very fast so that the surface speed of the roller is faster than your drivetrain can move. It basically just keeps game pieces from escaping to your robot if you're trying to, or escaping from your robot if you are driving like backwards while you're intaking or something like that. So, okay, so then basically when you're doing a system like this, you can't just position these anywhere you want. The spacing between the center lines of the axles basically have to be on a certain distance that is compatible with the belts and the pulleys that you want to use. There's a few different ways to kind of figure out what that is. I'm going to show one particular method today. But there's lots of different ways to do this. And if you may have other people that'll show you other ways of doing it, so don't take the method I'm going to show you today as kind of like the end all be all of designing with belt center to center distances. So essentially what we need to start off doing is we need to kind of pick a center to center distance that is close to what we want. So we need to just say we want it about whatever this is, right? 4 inches, right? Let's say we want about 4 inches between the motor and the first roller and the first roller and the second roller. Now what we need to do then is we need to validate that this dimension can actually be achieved with belts and pulleys that we select. So what we're going to do is we're going to use a center to center distance calculator and just try to find a number that's close to something we can actually achieve, and then we'll go back to this sketch and we'll edit kind of what's going on here. So let's go ahead and let's open a new tab here, and let's look at we're going to go to sdp-si.com, I believe. Yep. So these guys are basically an industrial like motion product manufacturer and seller. So you can buy all kinds of things from these guys. You can buy gears and gearboxes and belts and cables and conveyor components and just all kinds of stuff. It's kind of fun to browse their website if you want to, but and you can order some stuff that's applicable to First Robotics here, especially if you need some like weird belt or some weird belt size or something that's not available or something's out of stock elsewhere. These guys are a reasonable option. That being said, they tend to have a little slower lead time and higher cost than most FRC teams will want to deal with. The nice thing that these guys do have, though, is they have a really great center to center calculator. So if you go to Design Tools and you go to Center Distance Designer, it'll take you to a new page. It looks like this, and this is the calculator. So we're going to use this. There are other calculators that people have made specifically for FRC. There's a large number of them. I'm using this one because it's a little bit more. It's slightly more industry standard. However, if you have a different calculator that you prefer or something like that, that's totally fine. They're all about the same. Some of them have different features and other things. So, okay, so essentially what we're going to do here is there's a few different ways that you can input. You can put things into this. Essentially, it's kind of like I don't know. It's kind of like uh, doing an algebraic equation where like you can only have one unknown. So you can you can enter certain things, and you have to enter, essentially all but one thing. You can kind of ignore this ratio up here. Kind of this is something you could use if you knew a ratio and you didn't know what size pulleys you wanted to use, but I hardly ever use this, so you can kind of ignore this. So you basically need to select everything in each one of these rectangles except for one, right? And ignoring the ratio, of course. So essentially we need to pick what our belt pitch is here. We need to pick a pulley, we need to pick a belt, we need to pick another pulley, and then it'll tell us what the center to center distance is. Alternatively, what we could do is we could pick our belt pitch, we could pick our two pulleys, and we could pick our center to center distance, and it'll tell us what belt we need. And so we can kind of use that to kind of get closer to what actual belt size that we're going to use. Now, in addition, we actually need to know what belts are available, because this list of belts here are belts that SDP stocks themselves. However, that is not necessarily you don't necessarily want to buy them from SDP, and you might want to buy them from Rev or Vex or other FRC and FTC suppliers that have a more limited selection of belts. I know on RoboChargers we stock, every belt size that Rev carries and most of the ones that Vex carries. And so we typically, when we're designing a mechanism, we design specifically for those belts, and instead of going for some weird size that you can only get from SDP or V belt guys or something like that. So what we're going to do then is we're going to go to Rev Robotics, and we're going to go to Vex Pro, and we're going to pull up the belt pages. GT2. I hope this page, yeah, okay. So these are the sizes that Rev carries. I believe this is all of them. I think there might be. Oh yeah, no, it's right here. Okay, so these are the sizes that Rev carries, and then we need to find. Oops, I didn't mean to click that. Belts and pulleys, and we want the GT2 9mm wide. So we're going to use these GT2 timing belts. Like I said, we explained what these were, what the naming convention means, and all that stuff in a previous COTS highlight. So I won't go over it again. But the important thing that we need to know today is the belt has a 3mm pitch, center to center from tooth to tooth, and it's 9mm wide. The ones that Rev sells are also 9mm wide. They're essentially interchangeable. The nice thing is there's a little bit of overlap, if I remember correctly, between Rev and Vex's offerings, but they do carry some different sizes. So if you're looking at Vex and Rev, you get a broader selection than if you're just looking at one or the other supplier. So that's also something we'll be looking for. So let's see. Let's go back to our center distance designer here. Our desired center to center distance, I believe this defaults to inches, so I'm going to assume that. Yeah, it does default to inches. And then we're going to pick metric for our units. Oh, I see. I see. Okay. It's changes when I switch it. We're gonna metric for our units, and we're gonna do 3 mm GT2 for our belt pitch, and then our timing pulleys. So what we're gonna do is the motor pulley here is gonna be a 16 tooth pulley. That's a Rev product. Um, it's a neodymium pulley. If we go here, it is this guy here. This is the pulley we're going to use, and then the rollers are going to be driven by 24 tooth pulleys, and we're actually going to 3D print those pulleys, and we'll go over the process of designing those pulleys in this project. So um, I know that they need to be 24 because we used these size of rollers in previous years, and that's the size that works well. So I'm kind of just going off of experience there. You can kind of just take my word that 24 works. You can go up a little, up or down a little bit. You could probably make 22, 23, 24, 25, 26 work, like anywhere in that range. But 24 is just kind of nice because it gives you some round number gear ratios and stuff. Okay, so anyways, we need to pick this. So 16 is fine over here because it defaults to that, and we're going to select 24 over here. And it keeps our desired center to center distance. This 101.6 is the 4 inches we typed in. It just converted the unit. And then basically it tells us this is the belt that we need, 88 teeth. The little asterisk means it's not a standard size belt. And then it says that the actual center to center distance is 101.93. So it actually gets very close. You can't always get that close, but it gets you very close. So then basically what we need to do is we need to take this 88 tooth belt and we need to go look at Rev and Vex and see what the closest size is. Um, so Rev has, the 55 is pretty small. So Rev has an 85. That's pretty close. That's within 3 teeth. And then I believe Vex has a 90. Yeah, so Vex has an 85 and a 90 as well. So basically we need to pick between 85 or 90, and then that will get us where we want to go. So then what we do is we pick which one we want. I actually think I'd like the motor a little bit closer, so we'll go with the 85 because I know that we have all of the Rev belts in stock. So we'll select 85 here, and then our center to center distance will update. So I'm just going to Control C and copy this to the clipboard and go back to my sketch and just paste it here and then hit enter. Okay, and that's our spacing. Now, normally on a normal robot, I'd be a little more concerned with what this dimension actually is because, where this motor lives, depends on other mechanisms and things like that. So, I might need to play around with this a little bit more. However, for what we're doing here, because we don't have a super defined application for this, I'm just going to accept that it's good enough and we'll move on with our life. Now what I want to do is we need to do the center to center distance from here. So I'm going to go back to the calculator, 101.6, and then we're going to select 24 over here. So it's going to be 1-to-1 from this roller to this roller. They're going to be going at the same speed basically, which is exactly what we want. And then if we do this and we hit enter, this will update, and this one's going to say 92. So I'm going to say right off the bat, like we're kind of in the same range. We either need to be, 90 or 95. We could also, if we wanted to, save ourselves some work, we could also use the 85. If that worked for our geometry, you could try to standardize your belts and use all the same belt on a mechanism. That's not always possible. However, it is kind of nice because it means you can just buy a whole bunch of that size of belt, and then you have a lot of spares and things like that. You don't have to worry about, oh, is this the motor belt or is this the roller belt, because they're slightly different and you can't really tell the difference. So when you're designing with belts, that's something to keep in mind. You kind of don't want to have a ton of different sizes of belts. That being said, I'm going to go ahead and design with a different size of belt. We're going to go ahead and design with a 90 tooth and use that. So, center distance designer, we're going to select 90, and then it's just 99 millimeters even. When you're using like metric belts and you're using a 1-to-1 ratio, you're going to get a nice round number for the spacing, like 99 millimeters exactly. And it's actually going to be a multiple of the pitch as well. Like I said, I'm not really going to go into exactly why like exactly like the math and everything behind this, but you can actually do this math in your head pretty easily if you have a 1-to-1 ratio. When things get when you have a ratio like the 16 to 24 ratio, that's when things get weird and you basically have to use a calculator like this. You don't really have a choice. So anyways, this is our layout. This is what we're going to accept. This is good enough for what we're doing here. We're going to go ahead and end this part here. In the next part, we're going to start fleshing this out into some different parts and start modeling kind of the rest of our assembly. And then I'm going to actually rename this layout. And yeah, that's a good starting point. So I will see you guys in the next part.